It's so nice when it's graduate students because at least some will show their camera. When it's a class of all undergrads, I'll just see a sea of black squares, and store pictures that look nothing like the person, and no one asks questions. They're all quiet, and it's really depressing. So I'm glad this is not that. Okay, so now I will get my notes going here. Okay. Okay. So what's going on with this class? Because this is a rather strange class. I haven't actually done this before, this particular kind of class. Well, actually, I have done something like it, but this is the first time it's going to be something a bit more formal. So, because this grew out of how, because well, everyone here, except Nemo, everyone who was here last year, you all took part in another instance of Math 685. That was an introduction to numerical analysis, and it was done in a more informal setting, a very small group, very small class. And there was a desire for a class like that, just covering something different, and maybe something that's not so MATLAB heavy. And so I thought about what that would be, and a natural candidate emerged because, and I'll discuss that here as a motivation for this class. It's grown out of my experience with teaching introductory courses for undergraduates in ordinary differential equations. So okay, so teaching. So we have this introductory course. These known here as Math 285. This is a problem I run into whenever I'm teaching that class. All right. So first of all, you look at a typical textbook on the subject. The way that solution techniques tend to be presented is, whoops, can't type today. That they do a good job of showing, okay, here's what you do. Here's a step-by-step procedure for solving certain kinds of ODEs, like linear, exact, separable, higher order ODEs of constant coefficients, and so on. And that's all fine and dandy, but as a mathematician, I find this unsatisfying because a lot of ideas in presenting these methods, I feel like they're pulled out of thin air. That more could be done to build these methods from the ground up. Now, an introductory course in ODEs is not taken by just math majors, of course. You have other disciplines, a lot of the sciences, chemistry, polymer science, etc. And naturally, they're not really interested in those kind of details, and maybe that's why these books are often written that way. And what I would like to do as a mathematician, of course, is to dive into that, to really show from basic principles, here's how these methods come about. And when you're talking about higher order ODE, second order, third order, and up, to relate solution techniques for those higher order equations to ones that will have already been seen for first order equations, and also by rewriting as a system of first order equations. And when I've taught Math 285, sometimes I have taken some time to try to do that, but this takes me to the second part of this dilemma is that to do this properly involves some linear algebra. Now, I don't have a problem with that. I love linear algebra. It's one of my favorite topics to get into for any reason. But in this class, Math 285, that's a big problem. It's not a prerequisite for that class. I cannot assume that the students have had linear algebra. You only need to have calculus 2 for this class. So sometimes what I've done is I would get into linear algebra anyway, and I would make clear to them, okay, I'm just doing this for those students who might be interested, like math majors. I'm not going to put this on a test. I'm not going to put this on a homework. But some students wouldn't seem to understand that, and they get mad at me anyway. I'm serious. They would get angry with me for doing this. And it's like, why be like that? Try to teach people some stuff and blows up in my face. And so, unfortunately, when I'm assigned to teach that class in the future, which is not this year, I feel like I have to give up on accomplishing this during Math 285. So what I've done instead is, as a follow-up, I've offered this special topics course. So just as Math 685 is a special topics course for graduate students on computational math, 492 is special topics for undergraduates. And I cover these things there. But even then, and I would generally be working with one student at a time, because as a topics course, you don't really get many students in those. Don't get very far. So then it made me think, especially when some of you all last year expressed interest in having another topics course like last year. So what this can do is this can build on whatever foundation you already have in ODEs and linear algebra, but also show how the two work together very closely. And what if, based on where your career paths take you, if you end up teaching one of these topics, then this what you learn in this class could give you more of a background to build off of, and possibly inform how you teach these things. So there could be that benefit too. Okay. Now, how am I going to proceed? All right. Now, even though you all have some background, that may vary in ODEs, really, what I would expect is you've had this undergraduate background in ODEs and linear algebra. If you have any graduate background, that's great, but not necessary. But I try to assume not so much. And also, what I'm going to cover, I have no idea how long it's going to take. I don't know if it'll fill a semester. If it doesn't, I'll cover something else. We'll just see how it goes. So what I'll begin with, and the nice thing is, because I have no expectation about that, I can go really slowly. And that's why this class period is only 45 minutes too, because I like to have a break. I have class before this and class after this, and I want to have a good gap in between. Okay, so first what I will do is we're going to focus on linear equations here. And with linear first order ODEs, it also overlaps some with ODEs that are either separable or exact. So I want to review what is normally taught about those kinds of equations, at least with regard to linear problems. And I want to unify the different types. So in particular, linear, separable, and exact. Because in a typical ODE course, these are covered as separate categories and therefore separate solution techniques. But it turns out that the solution techniques you learn in a class like that really all come from one central idea, and that's not really discussed. So I'm going to discuss it. Okay. Then from that, I will move to systems. First order, again, linear ODEs that will use ideas from a single first order ODE, but it uses a linear algebra. And for that, we're going to be relying heavily on eigenvalues and eigenvectors. Also, we have to look at the cases of case where matrices involved are diagonalizable or non-diagonalizable. Okay. So in fact, we have to get into not just eigenvectors of matrices, but in some cases, generalized eigenvectors. Okay. And how what we learned here about a single ODE generalizes in a very direct way to a case of systems. And how we get to a matrix exponential. All right, that used to describe such solutions. And then what we have here after that, what I'm looking forward to the most is we get to higher order linear ODEs. And because we can reduce these to a first order system, so what, and the focus is on how to derive established solution techniques. And those techniques would be using a characteristic equation of higher order ODEs. Also, methods that you would have learned in a class like Math 285, such as method of undetermined coefficients. Also, a variation of parameters. Okay. Because again, with these kind of techniques, like especially method of undetermined coefficients, what you're taught is, okay, if this is your ODE, here's how you proceed. And there's no explanation as to why what you're given works. Well, in this class, you're going to find out exactly why it works. So these methods will be derived from nothing, but using what's covered prior. Okay. So that's the plan. We'll see how this goes. Now, what about what is it that you will be doing besides trying to absorb whatever I talk about here? Okay. Now, I have not fully fleshed that out yet. So there will be homework problems. I'm not going to have tests in this class. And I probably will not be giving homework very quickly, like maybe not during like this week necessarily, but okay. Now, so maybe something where I'm covering a certain topic, and I think, you know what, I've shown things up to a certain point, but now here's something that, based on that, I'd like you to show, and that could be a homework problem. So how many there will be, or how often, I have no idea. This is all very impromptu. So while I have a concrete plan for what's to be covered, as far as the course we can branch off of that, we'll see. Now, oops, this is totally misspelled. Okay. Because I actually have written up some notes about these things. I've not put those notes out yet because I need to review them and see, like, well, what if there's certain things in these notes that I feel like should be homework problems? So I need to go through that first because I don't want to put out some notes that give away what might be a homework problem. But I'll try to review those as soon as I can, and then anything in there that is not homework, that I'd be fine with posting on campus. So, okay. All right. So, are there any questions at this point? Like how the course will be run? Although I might not really have much to offer about that. Okay. Now, that because I want to have half-hour break between class periods, that as of this moment, I only have 18 minutes left. Not that I had much planned for today or any day. It really doesn't matter. But at least I can attempt to get the ball rolling. Okay. Now, all right. So we're talking about a first order ordinary differential equation that's as general as possible. Okay. Whoops. All right. And then I'll throw an initial condition. Okay. And the idea is, okay, I'm going to start this one and move this to a new page. All right. All right. And I want to describe a solution of this ODE implicitly. So we have some unknown function, capital F, that depends on t and a solution y of t that satisfies this equation. So then, if I apply the chain rule to this, then what I'm going to have is, okay, so partial f with respect to t plus, dang it, partial f with respect to y dy t equals 0. Okay. So, all right. So what I would like to do ideally is, since this equation has a dy dt in it, and so does this equation, then I would like to match these up in some way, so that maybe from the known function little f, I could somehow figure out what the unknown function capital F would be. All right. Now, I think all of this right now is well, not entirely improv, because it's based on things that I've covered before, but what I'm doing now is only, I guess, moderately planned. Okay, now, let's see. Actually, I'm going to cheat here for a second and look at something I have in another window that will help me here. Okay. All right. Because it might be helpful to make some assumptions. So right now I have the most general ODE. I might want to narrow it down a little bit. Okay. Okay. All right. Now, so what I could do is if I try to match these two up, then I could say that y prime is f of ty, but that would also be minus df dt over df capital F dy. Just from rearranging it and solving for dy dt. So what we'd like to know is, okay, if this is known, how can we find a function capital F that will satisfy this? But considering the complexity of this equation, generally it'd be very difficult just to find some function capital F that matches this for an arbitrary little f. But what we could do instead is change the ODE. And we can perform whatever legitimate algebraic manipulation on this, and maybe get an equation that's easier to solve. So what I'm going to do is I'm going to all right. First write this equation in a way that more closely resembles this one. So I'm going to move little f over to the left side. All right. And now I'm going to scale this equation by some unknown function, mu. Okay. So although it might be too difficult to match this equation to this one in a way that would reveal what capital F is, maybe instead I can match this equation with this one. All right. So now I have derivative capital F with respect to t must be equal to minus mu times f, and then partial of f with respect to y must be equal to mu. Okay. So for instance, maybe depending, what if I could find a function mu that would make this equation simpler, and then I could solve for capital F by integration. All right. Okay. So now what I can do is I can take this equation and differentiate with respect to y. This equation differentiate with respect to t. Okay, so now what I have here is, so here I have a second partial of f with respect to t and y, and that'd be a derivative of this with respect to y, so that'd be minus mu yf plus or minus mu df dy. And we differentiate this equation with respect to t, so that'd be f yt is equal to mu t. But under assumptions of continuity of second partial derivatives, these two must be equal. So now capital F is eliminated. Okay. So ut is equal to u fy. Okay. So from the known function little f, if I could find an unknown function mu that depends on t and y that satisfies this equation, then once I find mu, I could integrate with respect to y and get capital F, except for one term that depends only on t. And then I could use this equation in combination with it, so these two together, to solve for capital F by integration. So okay. So more specifically, what I would have is F would be the integral of mu with respect to y coming from this equation plus dang it, plus some unknown function that would be dependent only on t. And then, okay. And I'm going to write this as m of ty plus g of t. So capital M here is this integral, so the antiderivative of mu with respect to y. And then what I could do is what I get here, I could substitute into this equation. Okay. So that df dt would be equal to mt plus g prime is equal to minus mu times f. And at this point, mu and f are both known. So so that would help me figure out, and the thing is, at this point also, this is known. So really what I'm solving is g prime is equal to minus mu f minus dm dt. So really, I'd solve this for the portion of capital F that I don't know at this stage. Because then I'd have a function capital F that would describe my solution. Now, once I have capital F filled in here, if I'm able to solve this equation to isolate little y of t, then I have the solution y of t explicitly, but that just depends on the function capital F that you have. Okay. All right, so this is our starting point where we try to find some solution formula, even if an implicit one. And it turns out that various methods for solving first order ODEs are normally taught in introductory class: linear, separable, exact. All of those methods come from this framework. The only difference between them is that for those classes of equations, you have different assumptions about little f. Like maybe you assume that little f has a certain form, and if little f is of that form, then this equation simplifies, and then you can get an explicit formula from u, and therefore you get a formula for capital F. So what I'll do, and I'm about to run out of time, is on Thursday, I'm going to show how this framework can be used to derive all three of those distinct methods for solving certain classes or categories of first order ODEs. And while we're most interested in linear, you'll see how it works for separable and exact equations too, even ones that are nonlinear. Because I've not made any at this point. I've made no assumption whatsoever about little f. But once we start making assumptions, then this procedure would become more concrete. Okay. Okay. Now, oops. All right. So, are there any questions about what has happened up to this point? I hate when this editor does this. All quiet bunch, huh? Okay. Now, aren't I just seeing like literally all of you in the next class? 560, I believe.
I'm pretty sure.
Yeah. Well, yeah. I'll just do a second roster, but yeah, all four of you are in there. Well, four of you and several other people. I will see in that class in a half hour. So that's going to be interesting too. Okay. So well, we got the ball rolling at least, and I will. I'll post a recording of this and the notes in Canvas. It might not be right away, but it'll be sometime tonight.
Thank you, Dr. Lamb.
Yep.
Hi, I have a question.
Oh, okay.
Is there a particular reference book that you can recommend?
Okay. Well, certainly, for what I'm covering at the beginning, well, actually, well, sort of introductory texts on ODEs would provide useful background material because I'm going to be taking those methods and just presenting them in a different light. But let's see. For what we're seeing a little bit later when we get to systems, an introductory linear algebra text that has decent coverage of eigenvalues and eigenvectors, like it also discusses generalized eigenvectors.
Mm-hmm. Okay. All right. Right. And I do wish to write you about the ODE class. I think the class of ODE is open now. I was just in Southern Hall and somebody told me.
Oh, still. The other. Dr. Tian's class.
Yes, Dr. Chen.
Oh, okay.
So, okay, well, thank you very much. I will see you in 30 minutes.
Okay, alrighty.
Okay, bye. Bye, guys.
Bye, nice meeting you, Nemo.